Wonderful.
So can you please share your screen? We'll just confirm.
Yeah, just give me a second.
I'm sorry, I just saw your message.
No issue.
In the chat box.
This meeting is being recorded.
Yeah, you can see it.
It's perfect, Professor.
And this goes to full screen, right?
Yes.
Okay, wonderful. So I'll keep the microphone muted for time being, and just let me know when to get started.
Sure, Professor. Sure. Thank you.
Yeah.
Professor, you can get started.
Okay, wonderful. So I hope I'm audible, and you can also see my video and screen. So
yes,
okay.
Please go ahead.
Yeah. So thank you, Ramashankar. Well, I was not very sure about who the audience is going to be for this talk. So I prepared sort of a general introduction to superconducting qubits. And I'll begin with some very basics, some key concepts, and then try to expand it, connect it to the ideas that how to control superconducting qubits and how to perform measurements on those, and how these small ideas can be used to understand how to run quantum circuits on such devices. So this will be at a very introductory level. And I'm not sure how the question answers will be handled here, but I'll try to leave some time at the end so that if there are questions, I can answer them. But yeah, so leaving that aside, so like I said, the outline of the talk is at an elementary level. So I'll begin with key concepts, explain what quantum bits or qubits are. And there's a very nice geometrical representation how to visualize quantum states of qubits. And then I'll move to, let me just get a laser pointer. Yeah. I'll move to what are different physical systems where qubits can be realized, and what are different type of qubits, and then we'll get into details of superconducting qubits. Along with it, we will study or we'll discuss transmon, which is a particular type of a superconducting qubit, a little bit more in detail. And then following these ideas, we'll learn a little bit about how to do control of a single qubit. And what it means is that if you want to prepare a particular quantum state in a qubit, how to do that. That's the idea here. And once you have those states, how do we verify that we are able to prepare those states? So that's a part which is related to readout of a single qubit. And then towards the end, I will try to explain what 2-qubit gates are and how these simple ideas then can be implemented to run a quantum circuit. So that's the overall outline of the talk. So To begin with the key concepts, I think I'm sure most of you would be familiar with what classical bits are. So in our traditional quantum computing, you can follow Boolean algebra and carry out certain tasks. And physically, these bits are realized by like voltage levels in transistor, or they could be magnetic moments. For example, hard disk, when you read the data, that's where the magnetization of a moment is read. We can assign labels, for example, to these states, 0 and 1. There are only two labels that are allowed. That's why the word bit comes in picture. And these are the only two possibilities. Either the system could be in 0 or 1. It cannot be a mix of the two. So it's a well-defined set of states that classical bits can take. When we perform measurements on this, and if we get an answer corresponding to 0, it means the system was in 0 state. And if we get an answer 1, it would definitely mean that system must have been in 1 state. So there is measurement process which is completely deterministic. On the other hand, when we think about quantum bits, these are like extended version. It's qubit is an acronym which is for quantum two-level systems, the quantum bit. In short, you call it qubit. Here, the labels are the eigenstates of the system. For example, they could be 0 or 1. And the allowed states here are much larger compared to the classical bits. You can have 0 and 1, these two eigenstates. But also, any linear combination of these two states is also a valid state. Okay, so that is also allowed state. So here the two numbers alpha and beta, they could be two complex numbers, and with some normalization constraint, we can form a linear superposition of 0 and 1, and that's an allowed state. So, remarkably, it's like very different from what we just said about classical bit. Here, the allowed states were just 2, 0 and 1. Here we have a very large possibility of allowed states. Yeah. So these 0 and 1, these are just labels in some sense. You can form a sort of a linear algebra with them by using these vectors to represent these states 0 and 1. Okay. Yeah. If when you perform measurements on such quantum states, if you have prepared, for example, a superposition like alpha 0 and beta 1, when we perform measurement, we get a single outcome. Okay, either it will be 0 or 1. The meter which is measuring this quantum state will never show you a superposition. Yeah? It will show you a deterministic answer that it has measured 0 and 1. But if we perform this measurement on the same state by preparing the system in the same state multiple times, then sometimes we'll measure 0, sometimes we'll measure 1. And from those distributions, we can infer that probability of measuring 0 would be something like alpha squared, and probability of measuring 1 would be beta squared. So here the important point that I'm trying to emphasize is that the measurement is probabilistic, yeah? And measuring those probabilities by preparing the system identically, we can learn about what is the fraction in the superposition for 0 state and for the 1 state. Okay, so that's one stark difference for quantum bits. Here is a little bit of a scribble I did today, just to sort of so the handwriting may not be the best here, but it's just to demonstrate the difference between classical and quantum gate. So in classical computing, we have different type of gates. For example, NOT gate, AND gate. In digital electronics, you must have learned these things. And then we have universal set of gates like NOR gate or NAND gates. So there is a way to sort of look at these gate operations. For example, consider a NOT gate. So if we label the input state 0 as this column vector 1, 0, or the input state 1 as a column vector 0, 1, then this operation of NOT can be thought of as a 2 by 2 matrix which operates in these vectors. Okay, so if I operate this matrix on state 0, it gives me a 1. And if I operate this matrix on state 0, 1, which is this excited state, it will give me a 0. Okay, so point here I'm trying to make is that these classical Boolean gates that we study, they can be, think of it as a transformation, which takes a particular state and then cast it into another state. In a similar spirit, the quantum gates can be understood. Here, the input states could be, for example, a superposition. We can have these labels
This meeting is being recorded.
Which is shown in blue. And similarly, on the other side, we will have 0 minus 1 by square root 2. The point which cuts the y-axis will be 0 plus I 1 by root 2. And similarly, on the opposite side, we will have 0 minus I square root 2. The point I'm sort of explaining this is following, that these operation of quantum gates can be visualized essentially as movement of these points on this sphere. So, for example, if you want to understand the NOT gate operation, we can think of it as a rotation about x-axis by pi degree. So, if I am in 0 state, by rotating the state vector about x-axis by an angle of pi radians, you can get it to the excited state. And similarly, if the initial state is 1, by rotating it about pi radians about the x-axis, we can get to 0 state. So essentially, these quantum gates that we have here, they can be represented as rotations about x, y, and z axes, in terms of single qubit operations. Okay, so these are like some key ideas that we'll be using later also. All right. So there is another aspect to it, which is this parallelism. So in classical computing, for example, if I have n bits, so they could be just one n-bit state. So so you can have like a possibility of, depending on what is the length of this word, you can have all those possibilities. But when you do computing, you process essentially one word at a time. Okay, and if you want to do parallel computing, what you're asking is that you can parallelize the hardware and process all these possibilities together. So that's a classical parallelism. It parallelly by the same hardware, and the hardware is essentially following the rules of quantum mechanics. So this gets transformed into a new set of coefficients here, but all this has happened by the same single hardware. Okay, so that's a sort of a difference which is very important, between classical and quantum parallelism. Such things. So again, like some elementaries here with quantum is when we try to understand absorption and emission spectrum of atoms, for example, right? So for example, in emission spectrum, we may see a dark background, and then there are selected wavelengths that shows up these lines. And similarly, in absorption spectrum, it's the other way. Right. And, the modern physics understanding that we have for these lines is that, they're really showing the quantization of energies for the electrons which are surrounding this nucleus. Okay. And because of that quantization, anytime you have a transition between two consecutive levels, that correspond to a line in the emission or absorption spectrum. So the fact that these lines are at different wavelengths tells that there is an energy level spectrum which is not equally spaced. And this coupling between light and atom happens by the dipole moment of atomic dipole moment that couples to the electromagnetic field. Okay. So now, if you want to make a physical system where we can realize a qubit, the simplest thing you could say is that let's think about just the ground state and the first excited state of a natural atom. Okay, and I'll ignore the rest of the other energy levels as long as they are far away spectrally. So if we approximate an atom as a two-level system, okay, we can call it a qubit. And you can do that because these levels are not equally spaced. So that's like the simplest possible qubit one can realize. There are other type of qubits which can be realized by lithography on chip, etc. So, for example, you can encode information rather than for example, what we used here are the energy levels of electron in an atom. So those were the degrees of freedom that we used to encode a qubit. Yeah. So you can also use, for example, charge of electrons or the spin of the electrons in quantum dots. So quantum dots are like small size structures, and you can confine electrons in a small area with gated structures on a two-dimensional electron gas. And once you have electrons localized in a small region, you can either use their charge degree of freedom or the spin degree of freedom to encode two levels, and that will become like a quantum dot based qubit. So the silicon based qubit that people are trying, they come under this category, where the spin of electrons is used to encode the two levels that are required in qubits. This sort of a platform has some advantages in terms of coherence time, and then if these devices are being built by CMOS technology, then you can scale them to a lot of qubits very fast. Of course, there are limitations too. There are connectivity challenges, and then you can also have limitations in terms of dephasing times and 2-qubit gate fidelities. This picture here is a picture of I think some quantum dots. Here 2 qubits, and what I would like you to appreciate here is the length scale. So this little white line here is 50 nanometer. So you can imagine, like if we have to make many such qubits, this lithography has to be very, very precise, which is not a problem. But at the same time, there'll be too much of crowding of these wires, which will be used to define the qubits in a narrow space. Okay. All right. So these are spin qubits. There is other class, which is trapped ion qubits. You will be hearing more about them in the next talk, I believe. But the idea here is that you can have one electron knocked out from the atom, so that leaves a net positive charge, and that can be trapped by using some sort of microfabricated ion traps. So by applying DC and RF fields together, one can trap an ion which has a certain type of electronic energy levels, and you can encode information either in the electronic transitions, which will be of very high frequency. Remember, like our natural atom, the transition energy here is high, so that it comes in very high frequency range, like to optical wavelengths. Or you can also use hyperfine levels, where the electronic spin gets coupled with the nuclear spin, and there is a lifting of degeneracy. And those sort of levels can also be used. Those frequencies are typically lower. So you can have both type of qubits here, either in the optical frequency range or in gigahertz frequency range. The sort of a platform is very advantageous in terms of you can get very high coherence here. We'll learn a little about coherence a little later. And one can also achieve high gate fidelities. The caveats here are the slow operations, and then you also need a lot of lasers to do the readout, and also like some control in the fabrication of these microfabricated ion traps. Okay, and multi-qubit readout again is a limitation of these platforms. Okay, so let's come to the part of superconducting qubits. Okay, so these qubits are essentially again microfabricated, and they are fabricated with superconductors, and these are typically much larger in size. Okay, so take a look at the length scale here. This is something like 300 nanometer, much larger than what we saw in the spin qubit. Yeah, and then one way to understand the superconducting qubit is think of them as a nonlinear LC oscillator, okay, made of an inductor and a capacitor. And this inductor is a very special inductor, and we'll learn about it a little shortly. And the idea is that it's made up of superconductors, so it has very low dissipation, and with magnetic flux, one can also tune their frequencies. The other advantage that happens here is that by tailoring the potential well, I'll be explaining that in detail shortly. One can form bound states of charge and currents and use them as basis to encode the qubit. Okay, so here's an example which I'll come back maybe a little later. How the energy spectrum of such a LC oscillator changes and becomes like this. Ramashankar, sorry to interrupt here, but I see there are lots of lines on my screen. Is it possible to disable?
Correct, Professor. Yeah, I'm also seeing that. Soumya, can we do something on that?
Yeah. Okay, wonderful. Yeah.
Yes, sir.
Right. Okay, so just to continue, thanks a lot. Yeah, so just to continue, yeah, this is a typical energy level diagram for a transmon qubit, and this is something that I want to explain in detail. I'm guessing, there may be a lot of students who would be able to connect to this idea quite easily. Okay, so the bigger point I want to make here is that these sort of qubits are larger in size, so easy to fabricate and reproduce. Second thing is the qubits, the two states that we are using to call it a qubit are the bound states of charge or current. Those are the sort of energy levels we use. Okay, so let's come to the details of this transmon qubit. So before we understand this, there's an important sort of a concept that we can learn, which is about quantum harmonic oscillator. Okay, so think of a ordinary circuit like made of an inductor and capacitor. Okay, so it doesn't have any resistance. So that you can achieve if the circuit is made, for example, with a superconductor. The resistance could be so small that you can ignore it for all practical purposes. Yeah. So this is an oscillator which is linear. So if I were to write the energy stored in such a circuit, you would write a simple formula that is related to the charge on the capacitor plate and the current through this inductor, or the flux through this inductor you could define. So it's like Q squared by 2C and phi squared by 2L. Okay. So now if such a circuit is designed in gigahertz frequency range, in microwave frequency range, and you cool it down to very low temperature, something like 10 to 20 millikelvin, what you would find that, even if you don't put any energy in such a system and it is in thermal equilibrium with a bath which is operating at 10 milK, the thermal fluctuations would become very, very small. And if it were to measure, for example, the charge or the flux at this point, here the quantum fluctuations will dominate. Okay, so if a high frequency circuit is cooled down to very low temperature, it shows quantum behavior because thermal fluctuations become so small in comparison to quantum fluctuations. And there is a statistical mechanics of such a circuit that one can do. And what you can find that if you were to measure what is the mean excitation number, thermal excitations in such a LC oscillator, it will be given by a formula like this. And if you plug in the numbers, so beta here is 1 over kBT. And if you plug in these numbers like frequency and temperature, you'll find that mean thermal occupation could be very small, like 10 to the power minus 5. So what it means, this number being so small, what it means is that system will mostly be in its quantum ground state. Yeah. So if we have cooled it down to very low temperature and its high frequency, it most of the time remains in the ground state, labeled here as 0. Okay. And maybe 1 in 100,000 times, it goes to an excited state. That's the meaning of this. So just by making a high frequency circuit and operating at low temperature, I have a very nice way to initialize the system to its quantum ground state. Okay. So that's one aspect about it. There is another aspect about it, which is that, these two variables here, charge and flux, they are both quadratic. And, this underlying symmetry that both are quadratic here produce an energy ladder which is equally spaced. So if we ask what is the next excited state, or next further to that, what is the next excited state, they will be equally spaced. Okay. So, it produces equally spaced levels. So here it's difficult to sort of truncate such a system as a quantum 2-level system, because if I try to drive the transition between 0 and 1, you would end up driving other transition too. Yeah. So you can't really approximate a harmonic oscillator as a superconducting qubit. Few other things that why superconductors become necessary, like I said earlier, because of low dissipation, you can achieve high quality factor in such resonators. The other fact is that, it's a macroscopic quantum state. So this node flux that we define here, along with other superconducting elements such as Josephson junction, makes it macroscopic. Yeah? So we don't have to worry about many other smaller degrees of freedom. We can deal here with a single variable phi. Okay, so these are advantages of using superconductor. So before we understand how to make a qubit, I think it's a good idea to get clarity on Josephson effect. Okay, so this is an interesting effect that happens when you put two superconductors separated by a thin insulating barrier. And the physics here says that, Cooper pairs, which are the sort of a carrier particle in a superconductor, can tunnel across this insulating barrier. Okay, so try to appreciate this a little bit. that if there is an insulator in between, there should not be any current that should flow between two superconductors. But if this insulator is thin enough, we can have quantum mechanical tunneling, and system can Cooper pair can tunnel from one side to the other. And this process can also happen reverse. From this side, the right side, Cooper pair can also tunnel to the left side. Yeah, so Brian Josephson, who won Nobel Prize for this pioneering work, derived these relations, which dictates how the Josephson effect current voltage relation should be. And the first relation tells you that there is a maximum current which can flow through this, and that's IC. And what this does is that if you try to push a current I through it, the system, the two sides of the superconductors will develop a phase difference given by this parameter phi. Okay, so phi is the difference of phi left minus phi r. Okay, if we try to push current more than the critical current, this junction will also develop a voltage which will be given by this. So it's h bar by 2e, and then time rate of the difference of the phases on the two sides. Okay, so if we look at these two relations, we can sort of derive very simple thing here, that by taking a time derivative of the first one, we can find a relation like this. And what this relation tells you immediately, that we have a circuit element here where voltage is proportional to the rate of change of current. Okay, so any electrical engineer at this point would say that this is the equation of an inductor, right? But this is a sort of a special inductor. Here, the inductance value depends on cosine phi. And if you think about cosine phi, it depends on I, the injected current. So we have an inductor here where the inductance value depends on the amount of current that is passing through it. So that's why it's a nonlinear in current inductor. Okay, and this is going to be an important point in understanding the transmon qubit later. Okay, the other thing that we can work out from here, these two relations, is the energy stored in the junction. Yeah, so if we take a product of these two relations, that will give me power, and I can do its integration over time to get an energy. So the free energy stored in the junction, if we just multiply these two and integrate over time, will be proportional to minus Ej cosine phi, where Ej is nothing but h bar IC by 2e. That's the linearly proportional to the critical current of the junction. Okay, so this is again like the potential energy equivalent for the Josephson junction. Okay, so what this effect does, it provides you a nonlinearity without any dissipation. Okay, so of course everything becomes nonlinear at large enough power, but here the key is that it's a dissipation-less nonlinear inductor, and that's the key to understand superconducting qubits, why they work. Yeah, it's a dissipation-less nonlinearity that we are introducing. Okay, so if you want to understand dynamics of Josephson junction, then you can also write down the classical energy of such a junction. And if, for example, it will have two contributions. One is coming from the potential energy, like we discussed, that is minus Ej cosine phi, plus there is going to be electrostatic cost of tunneling. So, for example, when a Cooper pair tunnels from left side to the right side, it leaves a plus 2e charge behind. Yeah, the two sides may be neutral to start. So it will leave plus 2e charge behind, and then this other island will have net negative 2e charge. Okay, so this process cannot continue forever because, at some point the electrostatic energy that will build up has to come from somewhere. Yeah, so that energy can be accounted by, Q squared by 2c, where Q is the amount of charge that has tunneled from one side to the other, and Cj is the capacitance between these two islands. Okay, and of course, charge is tunneling in terms of pairs, which are Cooper pairs here. So we can write Q as 2e times the n. And if we do sort of some restructuring of this, we see that there are two energy scales that are coming in the picture. One is set by the Josephson energy, which is Ej. That's telling us how the wave functions on the two sides of superconductors across the barrier are mixing with each other. That's the Josephson energy. And there is another energy, which is energy scale, which is this EC. That's basically setting up the electrostatic energy cost when tunneling happens. Okay, so depending on these ratios, whether Ej is large or EC is large, we can have different sort of dynamics of this Josephson junction. And given the fact that this number and superconducting phase difference are two conjugate variables, one can think of it like, this is the potential energy and this is the kinetic energy equivalent in this. And if you want to go to quantum limit, we sort of assert that, these n and phi, they follow this sort of a commutation relation and they do not commute. And then we can promote them to operators and write down the Hamiltonians, etc. Yeah. So the other way to, very nice way to visualize is that you can think of it like, there is some phase particle here. So this horizontal axis is phase, that's phi here, phase difference. And there is a potential, which is minus Ej cosine phi. That's what this wave is representing. That's the potential energy. And, there could be a particle which has a kinetic energy given by 4Vc. So if the kinetic energy is too high, then this particle may be hopping across many, many wells. But if the kinetic energy is small, this will remain localized in one of these minima. So that's like, again, a visual cue to understand these two energy scales. Okay. So having this part clear, one can now easily understand what a transmon qubit is. So what you do in transmon qubit, you take a Josephson junction represented by this cross here, and then shunt it with the large capacitance. Okay. So now you see, one could operate such a circuit in a limit where Ej, which is the equivalent to potential energy, is much, much greater than Ec. That's the kinetic energy. Right? And if we think about, this earlier picture that I had, that, we can imagine a fictitious phase particle. And if we compute its energy, then those energies will be something like this. But now we have modified that harmonic potential that we had for a linear inductor to a cosine-like potential. So if I write down the total energy, there'll be a kinetic energy term minus a nonlinear energy term, which is minus Ej cosine phi. And that nonlinearity will create these levels in such a way that they are not equally spaced. Okay. So now if they are not equally spaced, then I can again do my approximation that say that the lowest two energy states are the qubit states, and we can truncate it, and that's the qubit subspace. And you can do that, like I said earlier, because now if you try to excite the system from 0 to 1 state, you can send a light which is at this transition frequency, and it will only cause excitation between this subspace, because other transitions are not tuned to this frequency, so they will remain unaffected. Okay, but it's so that's how you can make a qubit approximation. Yeah, so you encode information for a transmon qubit in these two low-lying energy states. Okay, there is another aspect to it which is important to sort of emphasize, and that is the notion of qubit enharmonicity. So it's basically asking a question that, there are multiple levels, but we are ignoring others and keeping the qubit subspace as only this much. But how good is this approximation? Okay, so that's if the enharmonicity is large, which is defined as the difference between two successive transition energies, then, if that number is large, then obviously you are making a better qubit. But if that number goes to 0, then essentially saying it's not a qubit, it's becoming more like a harmonic oscillator. Okay, so enharmonicity is like a good figure of merit to look for when we want to truncate a many-level system into a two-level subspace. Okay, so this is how the transmon qubit is realized. You take a Josephson junction and shunt it by a large capacitor, and you want to satisfy this criteria that Ej is much greater than Ec. Okay, so now that you have understood this part, one could argue that, all you are doing here is kinetic energy is fixed, that is decided by Ec, but I can play games with the potential energy. So if I tailor the potential well, from cosine to something else, I could realize other type of qubits as well. And that is completely true. Rather than taking a single junction that one could do in transmon, one can make a loop with asymmetric junctions. One could be a larger critical current junction, another two could be smaller critical current junctions. And if you do that and compute what is the potential for such a Josephson element, you will find that it can have this double well sort of a potential. And again, the fact that, this is not harmonic, it's not a parabola, you will have, energy levels which are not equally spaced. And you can again encode information into these lower two levels. And this is called a capacitive shunted flux qubit. You can do another variations. Rather than having two, one can make an array of Josephson junction. Sorry. And what you will realize there, rather than having like one local minima, you could get multiple local minimas, and that sort of a qubit is called a fluxonium qubit. And similarly, like, if you do a current bias to a transmon and choose its EC and EJ correctly, one can get this asymmetric potential profile. Asymmetry is coming from the current bias. And in this asymmetric profile, again, one can pick two energy levels and encode information there, a qubit state there. That will be a phase qubit. So point here that I'm trying to make is that by tailoring this potential well, you can change the potential and shape anything but parabola, and you can realize a type of a qubit. There is, of course, a reason why people would like to try different potential shapes, because some type of qubits may be more sensitive to charge noise or flux noise, and by adjusting these potential profile, you can make them insensitive to certain type of noises. Okay. So the other point here is that there exists a whole plethora of superconducting qubits. I have just taken some representative examples, but the philosophy goes in the same way, that you are trying to prepare a design and making it less sensitive to certain type of noises. Okay. All right. So having explained this idea of how to realize the physical system, how to realize these qubits physically, let's try to get to the basics of how do we control them. Okay. So I hope one part is clear to everyone, that if we want to initialize the superconducting qubit in its ground state, then the easiest method is just you wait. Yeah. So if temperature is low and frequency is high, like I said in one of the earlier presentation here, right, it will naturally come to ground state. Okay. So initialization to ground state is easy. You just wait long enough and it will relax to ground state. And that's an easy way of initializing it to the ground state. So as long as you meet the criteria, the temperature is low and frequency is high. Yeah. But you can start from an initial state which is zero, but then you want to think that how do I create the excited state? How do I take it to the excited state 1? Or how do I create superposition states, like some 0 plus 1 by square root 2 or something? Yeah. So that's the part which comes under control of a single qubit. Now there are different ways you can look at it. Like the abstract way of looking at it is that you have a two-level system. You can label them as 0 and 1. They have two energies, minus h bar omega q by 2 and plus h bar omega q by 2, so that this transition frequency is omega q. Yeah, h bar, or this energy is h bar omega q. Okay, so that's one way. And then if you want to sort of control this, we can shine a microwave pulse and calibrate its amplitude and duration in such a way that it takes you from 0 to the 1 excited. That's one way to think about it. When you're thinking it more in terms of hardware, you will have design something like this. This plus shape here is the superconducting qubit. Ignore this meandering line for time being. I will emphasize it later. This is for the readout. But then you can bring in a line which basically capacitively delivers a microwave pulse to the qubit. Okay. And again, by controlling its amplitude and duration, one can manipulate this two-level system. So the physics of it is, of course, that if we were to understand it better, we can write the Hamiltonian of this drive along with the qubit. And what really happens is that a qubit can be represented as these two terms here, yeah, and then drive can be included as a term which connects level 0 to level 1 with the strength of this capital omega at a frequency of omega d. Yeah, so you can also have it slightly detuned from the qubit frequency. Okay, so this is of course a time-dependent Hamiltonian, and we can get rid of the time by going to a rotating frame at the drive frequency. And this is the part that you will get in interaction picture, where delta q is now the detuning between drive and the qubit transition frequency omega q. Okay. And additionally, what we see that we get two terms here. There's omega x with sigma x and omega y at sigma y. And essentially what these terms will do, they will create x and y rotation on the Bloch sphere depending on what the amplitudes of omega x and omega y is. One caveat is that something to keep in mind, that there could be effects which comes from the finite inharmonicity, and sometimes these pulses need to be tuned correctly so that the qubit doesn't leak outside these two levels, the qubit computational subspace. Yeah. In order to implement it in lab, what typically is done is that you use IQ mixers, and they can be implemented either in analog domain or digital domain. So those of you who are familiar with the IQ mixing, essentially what you do is you take a local oscillator, and you can have an I channel and a Q channel where the LO oscillator's phase is 90-degree different, and then you can combine the output of these RF and LO. Yeah, so what will happen, that any signal which is sent to I channel alone while maintaining Q will create, essentially, given that interaction we had, a rotation on the Bloch sphere about x-axis. And similarly, if there is no signal at I channel, but you have some signal on Q channel, you will be rotating the qubit about y-axis. Yeah, so remember that we had that Bloch sphere sort of a representation of qubit state. So in that context, I'm saying that just by shining a microwave through I or Q channels, one can control the amount of rotation about x and y axis. You can also implement rotations about z-axis just by introducing a phase shift in the LO input control. So that will implement a z-axis, rotation about the z-axis. Okay, so this is how it is done typically in the lab. And I have this little schematic to show that if we want to do a pi rotation about x-axis, that was our quantum node gate, if you remember. We can send a pulse here, which has a duration and amplitude tuned just right through the I channel. And if my initial state here is aligning with the North Pole, at the end of this pulse, it will be transferred into to the South Pole. Okay, so that will implement a rotation about x-axis by an amount pi. Similarly, we can also implement rotation about y-axis by sending no envelope through the I channel and use only the Q channel. That will implement a rotation about y-axis. So if the initial state is 0, we'll have it transferred into 1, but that rotation will be implemented about the y-axis. So this is one way you can visualize that that simple operation that we had as a matrix at the very beginning can be realized by sending microwave pulses. Okay, and this dynamics of qubit then can be visualized easily on the Bloch sphere through x and y rotation, x, y, and z rotations. Okay, so this is the pulse level control of a single qubit. Okay, so let me quickly, I think I'm running a little bit behind the schedule. Let me quickly explain what the qubit, how the qubit readout works. So readout means, you want to measure a qubit state. And like I discussed, you don't measure zero superpositions, you measure the eigenstate of the measurement operator. Now, in order to implement the readout of a transmon qubit, what you do is you take the qubit, which is represented here by this 2 junctions and this capacitor, and you put another mode and which couples to it through some capacitor, or it could be even inductive. Okay, so you can have sort of a 2-mode problem, and then if the system is designed in such a way that the qubit transition frequency represented by this omega 01 is very different from the readout resonator frequency, and by very different, I mean that the detuning here between these 2 modes is much larger than the coupling strength between these 2 oscillators. Okay, so this is called a dispersive limit, and it opens up a very nice way of doing the qubit readout. So if the 2 modes are dispersive, you cannot have a direct exchange of energy between them because their frequency is just mismatched. You cannot have a direct energy transfer. But what this interaction does, it basically makes the resonant frequency of this circuit here, which is the readout resonator, dependent on the quantum state of the qubit. Okay? And this can be understood by taking sort of a, asking the question, what is the Hamiltonian when you have an electrical circuit like this? And you will realize that if we treat transmon as a two-level system, we'll have a readout resonator represented by this A dagger A type term, and then a two-level system, but the interaction becomes diagonal. So we have A dagger A and sigma Z. So what it means is that if we ask the question, what is the coefficient of this term, A dagger A, it is omega R from here, and then chi into sigma Z. Okay. So now if sigma Z is +1, for example, that may be the case when qubit is in ground state, we will have this resonator frequency as omega R plus chi. But if qubit is in excited state where sigma Z has a value of -1, the resonator frequency will be omega R minus chi. So resonator frequency here means the coefficient of A dagger A. Okay. So that is quite interesting that there is no direct energy transfer. And despite that, by measuring this minor phase shift that occurs, I can tell what the quantum state of the qubit is going to be when it is in 0 or 1. So when it comes to readout, for example, we can drive the system at this frequency here, somewhere in the middle, and ask the question like, what is the phase shift? So if we measure that, we can send a readout pulse, for example, and it will come out either like this blue curve or this orange curve, which is behind it, with slightly phase and amplitude shifted. And if we integrate those IQ values, we can make, we can send multiple readout pulses and build these probability histograms. Okay. So this is one way you can detect whether the qubit has been found in ground state or excited state. And if you do many such measurements, you will measure the probability of detecting it in 0 or in the 1 state. One important point, like a term which you may find is used, is about the assignment infidelity. So as you can see that, there are, given some practical noise in the system, these points may be scattered. This may not be single points here. And the overlap between these two sort of a two-dimensional Gaussian curves is essentially the error where you are not able to separate, given a measurement, whether it was in the cloud of ground or in the cloud of excited state. So that leads to some sort of infidelity errors, assignment infidelities on the readout. Okay, so by drawing a line here, for example, in between which separates the two clouds, you can do a state discrimination on the qubit state. But the idea essentially is that you put another resonator beside it, and you keep on querying what is the resonator frequency, what is the resonance frequency of this resonator, and that has the information about what the quantum state qubit is in. Okay, so this is how the readout works. All right. So let's come to one more aspect. So far what we have seen what the physical system is, how to control it, how to implement a single qubit gate, and how to do the readout. In order to run quantum circuit, you need one more important ingredient, that is the ability to do 2 qubit gates. And, again, I scribbled something to quickly explain the concept. So a 2 qubit state, for example, will live in a 4-dimensional Hilbert space. So if we have labels for qubit 1 as 0 and 1, and similar label exists for qubit 2, we have a combination of these two, and the final result of possible computational basis state could be 0, 0, 0, 1, 1, 0, and 1, 1. And again, we can form the sort of a linear algebra for, representing these labels. If we had these 1, 0 sort of a vector, column vectors here, we can take a sort of a product with another one, and from a 2 by 1, we can go into 4 by 1 sort of a dimension. So these different states then can be labeled as, different type of column vectors. And essentially what these 2 qubit gate means is that, you have a column vector here, which is the initial state, which has 4 entries. And then you apply a linear transform of it. Those are the 2 qubit gates, which will have a 4 by 4 size. And it gives you another final state, let's say beta, with some new, coefficients. So in terms of 2 qubit gates, there are like different type of 2 qubit gates. The most common ones are, for example, like controlled NOT, which will have a matrix element, some representation like this. Or you can have control Z, where all the entries are in the diagonal, except the last entry in diagonal is -1. Or you can have swap gate, which basically swaps the amplitudes of 0, 1, and 1, 0 states. So here the ones are off diagonal in the middle. Okay, so these are like the representation of that 4 by 4 entries. So now comes the question that, when we were trying to understand single qubit gates, we could understand it through the IQ modulation by sending some pulses on I channels, Q channels. We could implement this rotation about X, Y, and Z axes. At a hardware level, what do we do to implement a 2-qubit gate? So of course, at hardware level, we need 2 qubits to start. Okay? And how do we couple 2 qubit becomes an important aspect on how we realize 2-qubit gates. So there are different topologies in which you can couple 2 qubits. For example, one simple could be that you take 2 qubits and couple them capacitively. Yeah, so this will sort of invoke an interaction between these two, which will be static, constant in time. Yeah, but that can be used, for example, to implement 2-qubit gate. You could have, for example, 2 qubits coupled by some sort of a resonator, like a bus you can add in between. So these could be 2 distant qubits and then talk via capacitance. You can, in this scenario, you can make one of the qubit tunable, for example. Or there are other schemes in which you can use a qubit itself to have interaction between 2 data qubits. And that's called the tunable coupler sort of architecture. So point here that I want to make is that there are many ways to couple 2 qubits together. It could be an inductive coupling, capacitive coupling, or you can use Josephson elements or circuits made from Josephson elements to mediate interaction between 2 qubits. Ultimately, you may get either a fixed coupling architecture or a tunable coupling architecture. And based on what interaction Hamiltonian has been used, one of these gates that I showed you earlier can be realized. Okay. So here is one example, where you can, use, for example, a parametric I-swap gate. So this is a design of some device. And what you see here, there are 2 qubits, one on this side. So these 2 pads are the capacitances, and then one can make junctions in between. Similarly, this is another qubit pocket where these 2 pads are the capacitances and a junction in between. And what is implemented here is that there is another qubit, right, in between, whose frequency can be modulated by sending a fast flux through this line. One can modulate the frequency. So if this qubit has a frequency of omega q1 and this has a frequency of omega q2, by modulating the frequency of this one can implement one can fill that missing energy and implement a I-swap gate. What you see in the measurement is the population for the Q1 and Q2 in the excited state. So if at t equals to 0, when there is no modulation, qubit 1 is initialized in state 1 and Q2 is in 0. When we do the modulation for a certain duration of time, we see that qubit 1 essentially comes to ground state and qubit 2 becomes to the excited state. So exactly at this point where my cursor is, one has implemented a swap operation. And just to confirm that, this is indeed the case, one can continue to measure and do multiple swaps. Okay, so there's one way one can implement a parametric I-swap gate. Unfortunately, I will not have time to cover all different type of 2-qubit gates. But just like I-swap, a parametric version of I-swap, there are CZ and CX gates can also be realized similarly. Okay, so I'll come to the conclusion part. So now look at the global picture. We have some superconducting circuitry where we can make multiple qubits. And by waiting for long enough time, one can initialize this qubit to the ground state. Okay. Then what happens on hardware level? There is a there's a sequence of microwave pulses, which implements, different type of gates. These could be single qubit gates, or these could be 2-qubit gates. And that's the quantum circuit that you are running on that initial state. And at the end, what happens, you perform the readout and then measure some sort of a bit string which contains the answer. And then you want to run this quantum circuit n number of times so that you can generate enough distributions to sort of get the answers of the calculation. So this is the overview that I want to give you, how computation happens on a superconducting qubit platform. So we have a physical layer where all the superconducting circuitry is sitting, and then there is an initialization, and then computation happens by a sequence of microwave pulses, and ultimately you perform the readout of qubit by doing certain state discrimination. Okay, so this is the summary of the talk. I hope I have been able to convey you some key concepts that are used in quantum computing as well as in the context of superconducting qubits, and hopefully the idea behind how to control single qubit, how to do their readout, and some rough idea about how to implement two qubit gate has been conveyed. I have not given you any sort of a comparison on where the superconducting qubit stands in terms of other platform, etc. I have kept those details out. The idea here was to give more introductory and a talk which will connect to the hardware. Okay. So I hope you learned something from here. And if there are questions, I'll be happy to take them now. We have, I suppose, a couple of minutes.
Thank you, Professor. Thank you. Professor, the question and answers are posted in the Q&A window. Will you be able to access it? There are about 16 questions.
Okay. So first of all, I need to stop share, I believe, and more. Is there a way? Can someone help me? I don't see the Q&A window. There's a chat window.
It's down there, Vibhor, in the Zoom window.
Yeah. Got it. Q&A. Got it. Yeah. It's hidden under more. Yeah. Okay. So is getting 0 and 1 is random? Yeah. So I think this question is in terms of, I suppose, the quantum computing part. Yeah, it is random. It's stochastic. Yeah, it is random. But then, it's random, but the probabilities, they follow a pattern. They still follow Schrodinger's equation. So, the evolution is deterministic, but the process of measurement is random. Okay, I didn't get the difference between classical NOT gate and the quantum gate. Yeah, so the way I actually quoted this example was to make a connection to the classical NOT gate. But you see, there is a lot more possibilities that exist for quantum gates. The example that I gave you is just a very ordinary one, where you can see that there is not much of a difference between classical NOT and quantum NOT. But imagine this, that you can also get square root NOT gate in quantum mechanics that has no classical analog. So the possibilities are far more. The example that I gave was just to make a connection. Why it is theta by 2? Oh yeah, that you can, well, it has some answer related to that. It's a spin half system. But if you follow the mathematics of the polar coordinates, it will naturally come as theta by 2. I don't think I can give a hand-wavy answer to this. Okay, is there any numerical derivation for North Pole as 0 and South Pole? No, this is just a convention. You set 0 somewhere and 1 here, but because students are familiar with spherical coordinates, it becomes easy to just put the North Pole as 0 and South Pole as 1. What is the meaning of gate fidelity? Very good question. So you remember, like I showed you, for example, for a single qubit gate, you are executing some pulses on I channel and Q channel. So if there is a mistake in the mistake in the amplitude of those pulses, the state that you want to transport, for example, from 0 to 1, will not reach 1. It will be a little bit off the South Pole. Okay. And that's the sort of a gate fidelity, that how closely you are able to evolve the system to the desired final state. Yeah. If there is a mismatch between the desired final state and what you have got, that's the error. And that 1 minus error is the gate fidelity. Quantum dots can be used in aquaculture, in environment monitoring, diagnosis. Okay, sorry, I don't know enough about it, so I will not comment on it. What happens if it goes to the excited state rare occasion? Yeah, so yes, so that's a preparation error. I think there's a question here. If the system once in a while gets in the excited state, that will be a preparation error. But again, like the idea is to minimize those errors. So by waiting long enough and keeping the temperature low, one can minimize it to like 1 in 100,000 sort of a preparation error. And actually one can do even better. Different quantum systems use different physical mechanism to encode information. So can they communicate with each other? If yes, how? It's a very good question. I think the requirements are very different. Best strategy that people are following is using light as the carrier between the different platforms. That's what I can think of. But it's a very good open question, like how to make different physical quantum systems to interact with each other. Okay, so how do we realize the phase operator in Josephson energy? Well, I think it will require some scribbling. If you send me an email, I'll be happy to send you some reading material on this. Okay, how weighting can bring the qubit in the ground state after reaching low temperature. So that's a very simple way would be that any system which is in the excited state would ultimately decay to ground state due to vacuum fluctuations. So just by weighting low enough, if there is not enough excitation, the system will get initialized to the quantum ground state. Unfortunately, I will not have time to answer other questions because I see Umakant is already online and my time is up. So I'll be happy if if you have
Professor,
some.
you have five. Sorry, Professor, you have 5 more minutes.
Oh, okay, fine. Let me see if I can answer a few more. So how will it help with superconductor IDK? How to superimpose these concepts to computers? Please let me know. Not sure if I got the question. Could you state why exactly only microwave pulses are used in the circuits? Yeah. So remember, these superconducting qubits that we make, their transition frequencies are in gigahertz range, and that's the range where microwave pulses would come in. Yeah. So if you take, for example, optical qubits, I think Umakant might talk about them. Then I guess it will be laser pulses equivalent. Okay. Do you also have an IC profile page where we can? Okay, TK, send me an email and I'll be happy to answer. Explain more the swap gate, like how it works on 0 and 1 state. So swap gate, remember, like will leave. So it's a 2-qubit gate, swap gate, I swap gate. So it doesn't really change 0, 0 and 1, 1 because even if you flip them, it remains the same state. But state, for example, 2-qubit state, for example, like 0, 1 or 1, 0, it will interchange their coefficient. So if you remember the matrix I showed, the 2 entries in the middle of that matrix were actually off the diagonal. Yeah. So that's like if you do that math, you will see that it ends up swapping the coefficient of 0, 1 to 1, 0. Okay, all right. For building a quantum computer, would the knowledge of VLSI design significant or not? Well, I doubt that, unless you are working with semiconducting qubits, I doubt VLSI design is significantly required. What are the advantages of superconducting qubits over other methods of generating qubits? So I suppose the question is, superconducting qubits, do they have a particular advantage over other platforms? So they certainly have some advantages because these are large in size. So lithography-wise, they are easier to fabricate. Control-wise, microwave, again, not very difficult to handle. Coherence-wise, they are reaching almost as good as the ion system. Like, IBM has results like where, they get 1 millisecond long coherence times. And then further, I suppose, the gate fidelities are improving quite a lot for superconducting qubits. So I can list several things here. But again, like if you talk to somebody else, they will have similar claims for their platform. So I think one has to be more practical about it. So that's the answer I can give. So question on telling me a difference between harmonic oscillator and a quantum harmonic oscillator. So there's no difference. It's just that they are operating in different limit. When you have too much thermal fluctuation in an oscillator, that will happen, for example, at room temperature, the quantum behavior will be masked by thermal fluctuations. But if we take a system to low enough temperatures where thermal fluctuations are gone, you will still have some fluctuations left due to quantum mechanics. And then we start calling it a quantum harmonic oscillator. So technically they are the same, but just operating in the different limit. All right. Does it mean that we can create a qubit using unequal energy levels? Yeah, absolutely. So in fact, anytime anyone say that they have a qubit, the first question you should ask them is what is the degree of freedom that you are using to encode the qubit states? All right, let me see if there are. So there's a question about what about the T1 and T2 times? Sorry, I have not been able to put up those slides, but like I said, the T1 times are excellent in superconducting qubit these days. There are people who are reporting like millisecond coherence time, which is as good as trapped ion systems. how heat or any physical noise disturbs the quantum system. Yeah, it's basically adds error in terms of the initial state preparation and how the state would evolve. So noise is very important. We haven't really talked about it, and there is a whole field on quantum error correction, how to design, or how to encode information in multiple qubits redundantly so that they become resilient to the noise which is coming from the environment. So it's very important. I have not spoken about it here. Let's see. What if we change the coordinate like north and south pole? Does it impact the result? No, that's just a convention. It will not change the result. So I see there are many, many questions. Unfortunately, I would not be able to answer all of them. I must stop now. So Ramashankar, over to you.
Yeah, fine, Professor. Thank you. Thanks a lot. Thanks for the very interesting session.
Yeah, thank you.
Professor Umakant? Good evening, participants. Can you please update your display names? So because the participation certificate will be issued based only on that. We see some numbers and some special characters and all. Please update it.
Hello.
Yes, Professor. Good evening. Good evening, Professor.
Good evening. Hi.
Yeah.
Yeah. So can I share my screen?
Sure, Professor.
Yeah, just a moment. Can you all see my screen?
Yes, Professor. Yes.
Okay. So good evening, everybody. Just a moment, let me just hide this. Okay, I can't hide this top panel. Okay. So, good evening, everybody. I will talk about ion traps and their applications for quantum computing in this familiarization workshop. And I'm sure in the previous talk, you would have probably got a good idea about the basics of quantum computing, but there might be some repetitions, but please excuse me for that. So this picture gives a very nice overview about the entire quantum computing landscape. So it starts with what is the difference between a classical and a quantum computer on the top left here, going down to the bottom. So somebody is annotating on the screen. Ram Shankar?
Yeah, Professor.
Yeah, somebody is annotating on the screen. Writing.
Soumya, can you please look into this? Can we disable this?
Oh, yes, sir, but I'm not able to disable the feature, sir. I have almost deactivated.
Okay, please look into that and then look into this.
Yes,
Yeah.
sir.
Please
Kindly
go ahead,
request
Professor.
participants not to use the annotate.
Yeah, please, participants, whoever are online, kindly restrain from writing anything on the screen while giving the talk, please. Okay, so going from the top left here, it gives a short description about what is the difference between a classical computer and a quantum computer and the principles on which both of these work, down to the physical realizations of quantum computers. Okay, and then there are things about various things going on in quantum algorithms area, looking at the entire usage of quantum mechanical systems, how those can be used to do real life problem solving in terms of coming out with algorithms which are quantum inspired or quantum mechanical, basically applying quantum mechanical evolution of states to achieve a particular solution to a problem. Now, today I'm going to talk about when the physical realization, and that too based upon based upon ion traps. So as this picture shows you here, there are these four rods here and then two discs on the end wherein you apply certain voltages and then you stabilize ions inside this like a linear array of ions, and then you use the internal electronic state of an ion for as a two-level system, the 0 and 1 and superpositions of those, and also entangling the states of the neighboring ions for doing quantum computing. There are other platforms like the superconducting platform, which you heard just now before this talk. Then you have neutral atoms, which are arranged in a kind of egg basket kind of potential where you organize these atoms in a periodic array and use them for doing quantum computing. And there are newer platforms that are emerging, which are still in very nascent stage, and that is looking at electrons which are trapped on the surface of liquid helium. And to some extent, NMR systems are useful for understanding how qubits can be used for quantum computing. Now, the basic criteria when you have to choose certain systems, certain quantum mechanical system as a for quantum computing have been laid out by DiVincenzo many decades ago. And this basically boils down to these very few simple qualifying criteria for a quantum mechanical system to be usable for a quantum computer. So first thing is you need to be able to initialize the state of the qubit. So the qubit has two well-defined states, 0 and 1. It could be spin up or spin down of an electron, or it could be an electron in one of the two energy levels which we will be talking about when you talk about atoms, or it could be two harmonic oscillator levels of a superconducting qubit, for example. Superconducting qubit in an LC circuit. It should have long coherence times. What this means is that when you excite the qubit to the excited state, or when you change the state from 0 to 1, again there is some scribbling going on the screen. Could you please restrain from scribbling on the screen, whoever is doing that? Thank you. You need to have a long coherence time. So when you excite the qubit to the excited state, it should remain there for as long as you want in terms of how much the time that you require for doing all your computation. So why does the qubit decohere? Because it's a quantum mechanical system, and because most of the times these two levels are some energy levels, ground state and excited state. The excited state in many of the atomic systems, for example, is going to interact with the environment, and it's going to decay back to the ground state after a certain time. Or if you prepare a state in a well-defined superposition of the ground and excited state, over time, the phase coherence of this state is going to get lost, and you're going to, basically the qubit will not remain a qubit anymore. So that is what this second criteria says. Then the third criteria is you should be able to apply you should be able to have universal set of quantum gates which you can apply on your qubits. Now, like what Vibhor talked about in the previous talk, this is about changing the state of the qubit or changing the state of a particular qubit conditioned upon the state of some other neighboring qubit. So these two gates are similar to what you have in electronics, which are the NAND gates. Once you have the NAND gates, you can prepare any kind of digital circuit, and you can use it as a microprocessor or a microcontroller or an arithmetic logic unit or whatever. Similarly, in a quantum computer, you need to have the basic gates are these two gates. One is you should be able to change the single qubit state from 0 to 1 or anywhere on the block sphere that Vibhor talked about in the previous talk. Or you should be able to apply a controlled NOT gate between the two qubits. At the end of all your gate operations on the set of qubits, you should be able to read what the state of the qubit is in. Okay, what is the state the qubit is in. So you should have a readability of the qubit. Then you should be able to scale up the system to increase the number of qubits, because for any practical problem, the number of qubits that are required are pretty large, and depending on the problem type, this can be very large or reasonable number. So these are all for what one calls a single node quantum information processing. That is, it's all for a single processor. Now, if you want to connect more than one processor, then you need to have something like in classical computers, when you put many chips and then connect them together and you make a cluster of a computer which is very powerful and which can become more powerful than just one or two computers. You need to have additional capability. So you need to be, in order to connect two quantum processors, you should be able to convert the quantum mechanical state, map the quantum mechanical state of the physical qubit in one place into a qubit that can be transmitted to the neighboring quantum processor, or a quantum processor which is very far away. So for that, you need to have an interconversion capability from the stationary qubit's quantum information onto the transmitted qubit. You need to have a channel over which this information can be transmitted. Like in electrical current, in classical computers, the information is carried as some voltage levels, which are logical 0 or 1, over some conductor connecting different processors. In this case also, you need to have a transmission line that basically does not allow you to lose any information that is going over that transmission line. So these are the two additional criteria for the distributed quantum information processing. Now, there are two broad classes of systems. One is quantum optic systems and the other one is a solid state systems. Solid state systems I already talked about earlier, the superconducting qubits and the other qubits like the electrons in either on a helium liquid or in a two-dimensional electron gas. I will focus mostly on this quantum optic system, and the talk today is on one of the quantum optic systems. What is a quantum optic system? Is basically wherever you use atoms and light. Now, these atoms could be in the form of either neutral atoms or ions, which are trapped in electrodynamic potentials. And there are other things like just photons, which are used for doing quantum information processing, wherein you have to do down conversion for getting entangled photons, or you have to do squeezing for generating certain states of light for doing quantum computing. Now here, this picture here, let me turn on the pointer. Yeah, so this particular system here is the ion trap system. This is a picture of fluorescence from atoms which are arranged in an array, which is used for quantum computers. Now today I will talk about ions in traps. Okay, so this picture here, what you see, these three bright spots in this picture, white bright spots, is an image of a real image of light that is emitted by single ions, and they are spaced by about few micrometers, about 5 micrometers from each other. And classical equivalent of that, a toy model, is something like these metallic spheres attached with springs together. So what happens is that when you try to shake one of these metallic spheres, the other ones will also start moving around, and the entire system of these three masses will execute some kind of simple harmonic motion, and there will be common modes of oscillations and so on. Now, quantum mechanically, so since our system is a quantum mechanical system, single atoms or single ions in this case, they are they are confined in some kind of a harmonic potential where these kinetic energy of these atoms is very, very small, or these ions is very small, so that they can be pushed to any of these vibrational states of the quantum mechanical harmonic oscillator, which I will tell you how it is done in the next few slides. So the plan of the talk is give you an introduction to these ion traps, how quantum information processing is done with these traps, and if time permits, I'll talk about quantum logic-based optical frequency standards with these ions. Okay, so what is an ion trap? So there are two types. One is this spherical quadrupole trap, and one is a linear quadrupole trap. This spherical quadrupole trap is nothing but, this is a cross section. There is a ring, and then there are two electrodes, hyperbolic electrodes from top and bottom. Now, depending upon the size of this trap, these electrodes have to be either perfectly hyperbolic, or they need not be perfectly hyperbolic. It depends upon the size of the trap and many other parameters. Now, if you apply a DC potential, for example, between this outer two electrodes and this ring, it forms a potential surface, something that looks like a saddle. Now, if you put a charged particle here in this DC potential, it's not going to remain there, because only along one direction the charged particle will be like seeing potential minima, whereas in the other direction it sees a potential maxima, so it can just roll off. But there is a way to stabilize that, and the way it is done is, when you start rotating this saddle, for instance, this ball will remain stable, will get stabilized in the minima of this potential, because in a time averaged sense, if you look at it, if you do a time averaging of a rotating saddle potential, it looks like a ball potential which is having a minimum in the center. Now that's how the charged particle in this trap gets stabilized once you add a DC potential once you add this DC potential to an AC potential, or you just have a AC potential, which is basically flipping between positive and negative polarity, or in a sinusoidal fashion between this so-called end caps and the ring electrodes. Now, this particular trap will can confine electrons or different kinds of ions depending upon the charge to mass ratio of these particles, the voltages that you apply, the amplitude of the RF that you apply, and the DC that you apply has to be calculated accordingly. Now, there is a different version of this same trap, which is a linear Paul trap, which is basically there are 4 rods like that, and you apply a AC potential between these opposite pairs of these rods, and you basically create if you just apply DC, you will create a quadrupole potential. But if you start if you start applying an AC potential, then it looks like a potential minima here in a time average sense. And this is a picture of a real trap from our lab here, where the ions are trapped in the center, and along this axis, you apply a DC to not let the ions fly off along this horizontal axis. Now, just quickly going through the little bit of math without a lot of details, just to give you a small flavor of what is happening is, so the electric potential, if you just apply a DC between the central electrode and these end caps, it's basically given by this quadrupolar type of potential. And since Laplace equation dictates that all the sum of these coefficients along all the 3 axes has to be 0, the potential is basically like a saddle kind of potential. Along one direction, the potential increases; along the other direction, the potential decreases. Now I'm talking about radial and the axial potential. However, if you add an AC voltage to it, this at a frequency of omega RF, then you start rotating this saddle, and then you create a dynamically stable point in the center where your charged particle will just remain stable. Now, if you solve the equations of motions for that particle, this Ri are the coordinates along the 3 axes. So this is just Newton's law of motion. If you write that, where Q is the charge of the particle and M is the mass of this particle, then these equations basically turn out to be nonlinear equations with certain, if you parameterize this equation, you get this AI and QI. These are basically parameters that are related to the DC potential, the amplitude, the DC potential, the amplitude of the AC potential, and also the frequency of the RF that you apply. Now, this leads to only certain parameters which will lead to stable solutions for this equation. And if you plot these values of A and Q, they give rise to such stable and unstable regions of the values of these parameters. Now, if you take this potential to be rotationally invariant, which is the case for this kind of a geometry, then along the X and Y direction, the parameters are the same. AX and AY are the same, and QX and QY are the same. However, in the relationship between AZ and AX are in this fashion. AZ is minus twice AX, and QZ is minus twice QX. Now, for very small values of AI and QI, you get the final equation of motion Ri, along R and along the Z axis to be this, where you get these frequencies omega I, which are called as the secular frequencies, and the parameter beta. The secular frequency is nothing but the frequency of the ion in that the time averaged kind of sense of potential. So, however, what happens is that since there is always a changing radio frequency, RF, that is changing polarity between the Z and Z axis and this R axis, there is always a small micro motion that the ion sees, which is basically uh, coming from the radio frequency. And if you neglect that micro motion, you can write down the equation of motion for the particle in a potential which is kind of static in time, which is called as a pseudo potential. You do the same analysis for this linear trap. Now, in this particular trap, you can only get clouds and three-dimensional crystals of these ions if you do laser cooling. If you just trap them, they will be at a very high temperature, several millikelvin or so, which are captured inside. But if you put laser beam inside it and use principles of Doppler cooling to cool these ions, then you can get three-dimensional crystals. But that is not what is desired for a quantum computer application where you want a proper controllable linear chain of ions. So you transform the geometry into this linear Paul trap. So you have these four electrodes for which to which you apply the radio frequency at certain frequency omega RF to the electrodes that are opposite, to pairs of electrodes that are opposite to each other, and you apply DC voltage across these tips. And there the potential basically you write along the radial direction, which is the cross section of this linear trap. The potential is time varying, which is along the x and y direction. It can be written like this, and along the axial direction, it's just a DC potential. There is no time varying component, but the total potential is what you apply along the tips and the these linear electrodes. So this is phi tip plus phi RF. So you do the same analysis again. You write the Matthew equations, and there the Q, and so here the coefficient is taken as B instead of A. Along the X and Y direction, the coefficient is the same, whereas the QZ is 0. The coefficient B is same in the X and Y direction. QX is negative of QY and QZ is 0. And this Q parameter is related to the amplitude of the RF and the frequency. Of course, the charge to mass ratio of the particle E by M. And R0 is the minimum distance between these linear electrodes. Now, once you do the analysis and write down find out the equation from the equation of motion, you find out how the trajectory of the particle evolves with time, then you get basically two sets of frequencies for the particle oscillating in the pseudo potential, that is along the radial direction and along the axial direction. So typically for the kind of traps that are used, the value of R0 is about little less than a millimeter. RF is in the range of 20-25 megahertz or so. So the radial frequencies are anywhere in the range of few megahertz for calcium ions, and the axial frequencies are of order megahertz or so, because you have to apply about a kilovolt along the axial direction. Now, there are many variations of these Paul traps which are used and for trapping these ions and creating a linear chain. So these are in this configuration A, you have the four rods, and for the axial electrodes, there are rings. Then in configuration B, you don't have directly the axial electrodes, but the pair of electrodes, the RF electrodes, are segmented, and you apply a small DC potential between the end segments of these two opposite rods. Or you have a trap where these electrodes are like blades, and there are axial electrodes like tips, and sometimes you can also have a hole through this tip for addressing the ions along the axial direction. Now, you can also fold this geometry and get configurations in a planar kind of a geometry as shown in A, B, C, and so on. So in the scalable ion trap quantum computer version, in the recent times, this planar surface trap is the most popular one, in which you can actually extend the length of this and have many series of electrodes along this, And these segmented electrodes are actually used for shuttling the ions along this line, and the RF is applied between these three center electrodes. So either the middle one is grounded, and with respect to that, you apply RF on the outer ones, or vice versa. Now the question is, why ion traps? So ion traps are one of the three leading platforms now for quantum computing. And I mean, apart from atoms and superconducting qubits, in case of ions, they are so very well controlled that they can be trapped in the trap for basically forever. You can trap them for even months if you want. If you load an ion, it can remain there for many days to weeks if you want. So you don't have to load these ions too often. You don't lose them while you are in the middle of some computation. The qubit transitions are all very well understood because these are natural systems, atoms and ions. Any atom of the same species you trap anytime will have the same energy levels. All the energy levels are very well understood. You can precisely calculate what would be the frequency shifts of these, what would be the decoherence rate, and many parameters you can precisely calculate from basic first principle atomic physics calculations. The lifetimes, depending on what kind of system you choose, the lifetimes of these excited states of the qubits can be very high, as long as seconds to many seconds. However, that depends again upon the gate operation times, which I'll not get into right away. The connectivity between qubits is also very important. So one of this, if you go to the planar geometries, like the one here as it shown in C, you can actually, as I said, can extend it into any kind of geometry. For example, this is a racetrack geometry from an earlier version of quantum computer developed by Quantinuum. You can actually move these ions. You can have zones where you can store these ions. You can have zones where you can make 2-qubit gates by changing the voltages on these DC electrodes, and you can just shuttle them around and bring any 2 qubits together and basically apply a 2-qubit gate. So which is what this particular diagram here shows. You can basically get a fully connected quantum computer with this kind of planar geometries. Now, when you have these ions in the trap and when you do laser cooling, you basically go down to the ground state of the trap, and the extent of this wave function of a single ion is very tiny, of the order of several nanometers, and they are basically localized point source of light emitters inside the trap. So this light here is collected with a very high numerical aperture objective, and it is imaged onto a CCD camera with some magnification, and the imaging is basically diffraction limited. Now these are individual ions, 2 ions, 5 ions, and so on. And this is a picture of up to 25 ions in our lab. The separation of these ions is about 5 to 10 microns, depending upon what is the axial voltage that you apply. And one second. Okay, I can't see just a minute. I'm trying to. Okay, I can't turn on this movie here of the quantum jumps. I'll try that later. So this video is about showing how to read the state of the qubit. So when it is bright, it is read as 1, and when it goes dark, it is read as so when it's bright, it's 0. When it's dark, it is read as 1. I'm trying to find the. So whenever the ion is bright, it shows the state is in 0, and whenever it goes dark, it basically tells us that the ion is in the excited state. And the way it works is this. So for example, in calcium ion, a particular isotope of calcium, which is calcium 40, this is the ground state of the electron, which is in S half state, and then there are many low-lying energy levels. So forget about all these blue transitions and these red ones. This orange one is what is important for driving the qubit transition. So you can drive from S half state to D 5 half state. So this D 5 half state is our qubit 1 state, and the ground state is qubit 0 state. The lifetime of this particular excited state is about 1 second, and this is an electric quadrupole transition. It's not a dipole transition like these other ones here in blue. So these blue transitions, like the 397 nanometer transition, is used for cooling the ion down to the energy where the kinetic energy is much smaller than the thermal energy is much smaller than the Coulomb repulsion between the two ions. So you basically crystallize the ion once you do the laser cooling, and then you have the quantum register, these bright spots of light that is emitted from the ions. And on each of the ion, you do the qubit manipulation by using this light at 729 nanometer. However, this has to be very, very narrow line width laser, which is technologically a very advanced laser system as opposed to any other lasers. And the way the state of this qubit is read, which I showed that time, bright and dark, is by a technique called as electron shell wave. So this is a picture that shows this. So you have a short-lived excited state and a long-lived excited state, which is our qubit transition. Now, whenever you have the electron excited to this state, you don't see any light emitted from the blue transition because you only look at the blue light. And whenever the electron goes and gets excited to this long-lived state, there is no light that is emitted from the blue transition because the electron starts from a common ground state. So it has either to go this way or this way. So this is a 3-level system, and you shell the electron in this state for detection. So if you do all your quantum mechanical the manipulation, the qubit gate operations on these two levels. There is another isotope of calcium. There is somebody else again doing this annotation on the screen. Could you please stop that? Please stop. Thanks. Yeah, so there is another isotope, which is the calcium 43 isotope, where because the isotope has a nuclear spin, the ground state S half, actually the total angular momentum of this ground state is not 1/2 anymore. It is 3 and 4 because of the addition of the nuclear angular momentum. And then you get 2 hyperfine ground states. Ramshankar?
Yeah, Professor. Yeah, it's annoying.
Yeah, it's quite annoying.
Correct, correct. Participants, can you please refrain from this scratching part?
1 second. Give me a minute, please.
Yes, Professor.
I'm sorry for the interruption, but it was quite annoying that people were scribbling on the screen. Okay, so this ground hyperfine separation between this f equal to 3 and 4, this offers an additional qubit. So earlier one, I think I'll stop my presentation, Ramshankar. Hello?
Professor, I have removed the person who is scribbling. Please go ahead.
There was another scribble now, just now.
Yeah, another one. I came, it got it. I've removed him. Please go ahead.
Okay. So if it happens next time, I will terminate the presentation. Okay, so this offers a microwave transition which also can be used as a qubit. So this transition is at around 3.2 gigahertz. And of course, there is an optical transition also, the 729 nanometers. So this particular isotope will offer you two types of qubit transitions, a microwave as well as optical transition. So how is quantum information processing done with these ions? So here, this two-level system that we will be referring to are this S and P state, which is this ground S state, and the excited D state will be the qubit transition. And we'll, for now, for the discussions in this talk, we will only refer to the optical transition. Now this S and D state. So once you have this ion in the trap, which is this harmonic oscillator potential, there will be motional energy levels in this harmonic oscillator potential, which have very well defined separation. And this separation is basically given by those radial and axial frequencies that I showed you in the beginning, of the order of few megahertz. Whereas the transition frequency of the atom is the line width of the excited state of this is less than a hertz. So the energy level separation of this harmonic oscillator levels is much higher than the line width of this transition. So once you put an ion in such a trap, then you can combine this energy level with the energy levels of the harmonic oscillator, and you can generate a ladder of these energy levels, which basically says that the first index here is not the index, but the first letter here denotes the motional mode. The second letter denotes the internal energy level of the atom or the qubit state. So S, D, motional mode 0. Then you have when you have the atom ion in the first excited state of this harmonic oscillator level, then you have the motional mode as 1 and the ground state S, excited state D, and so on. So you can generate a ladder of these energy levels. So where you are in this ladder is decided by where the ion is on in these energy levels. Now, the way you do qubit manipulation, single qubit manipulation, is if you do shine light on this S and D transition, then if you look at the physics of a two-level system, you are basically going to drive Rabi oscillations on this S and D transition. And this S and D transition are the two poles on the equator of the Bloch sphere, which is used for representing the state of a qubit, because any two-level system can be represented, the state of the two-level system can be represented on a Bloch sphere. And since the state is a complex, is denoted by a complex number, it's not just a circle, but it's a complete sphere. So there are phases associated with the vector on the Bloch sphere. Now, you shine light continuously on this S and D transition, you change the population from 0 to 1 to 0 to 1 and so on. So these are the Rabi oscillations that one talks about. So if I apply a pulse of light only for say half a microsecond, then I completely flip the Bloch vector from one pole to the other pole, which is basically applying a pi pulse. And if I apply this pulse for about a microsecond, then I go to from one pole to the other pole and back to the same pole. However, I'll pick up a phase of a pi when you do a rotation on a Bloch sphere. Depending upon how much solid angle you cover on the Bloch sphere, you pick up that much phase. Now, in these ions which are trapped in these traps, the typical sequence of measurement or applying a gate starts by, say, you keep the ion in the trap, you do Doppler cooling, you shine a laser pulse on the blue transition to cool the energy level, to cool the motional modes of these ions. Then you do a sideband cooling wherein you bring the ion to the lowest ground state of the trap, and then you do all your coherent manipulations like applying these gate pulses, and you do the measurement. Now, why are there these other ones like the motional modes? So when you have the ion in the trap and you excite with the light, which is exciting the internal state, you get one very sharp resonance at the at the transition frequency of the internal state of the ion. So you go from S equal to S to D. So there you get a strong transition. But then if your laser frequency is slightly higher, and if the the laser frequency is such that the energy is exactly equal to the internal energy of the atom plus the energy difference between these harmonic oscillator levels, then you go from, not only you change the internal state from S to D, but also you excite the motional mode of the ion. So these are these axial modes which you see at certain frequencies like 1 megahertz, and you also see the radial frequency which are at around 4 and 5 megahertz. So you excite radial as well as axial sidebands of this transition. So you can do Rabi oscillation on this S to D, plus you also can do a Rabi oscillation together on the, say, one motional mode, say in this case from 0 to 1 and so on. So these are the sideband excitation pulses. So the sidebands, the coupling is smaller because you have to, the wave functions of the excited state and the ground state do not perfectly overlap at the same point in space, so your coupling is lesser. It is decided by something similar to what is called as a Frank-Condon overlap in molecules. So in molecules also you can excite motion vibrational modes if you come with light of higher energy than the internal energy level of these atoms which have formed a molecule. So the string of ions is similar to a molecule. Now, this excitation to this blue sidebands, which means you go from a lower vibrational level to the higher vibrational level, or you can also, if you're on one of the higher vibrational levels, if you apply a red sideband pulse of lower energy laser, then your ion can come to a lower energy level. Basically, the extra energy is taken from the motional mode to excite the ion. So you can treat this system using these are the motional creation operators for the motional modes and the annihilation operators for the motional modes. These are basically harmonic oscillator creation and annihilation operators. And as I said earlier, the kinetic energy of these ions is much lower than the energy level separation between these motional energy difference between the motional modes. So this is done by laser cooling, as I said. Then you can basically apply a complete quantum mechanical treatment using these operators. And the harmonic oscillator, you can write the Hamiltonian for the harmonic oscillator mode. And in this harmonic oscillator, you can calculate the extent of the wave function in the ground state by just calculating the mean square of the displacement in the lowest motional mode, and that will be square root of h bar over 2 omega. So for example, the ion that we are working on, and just to take an example, I have taken this ion as calcium ion. The trap frequencies are typically about a megahertz or so. So the 0-point spread of the wave function of the ion in the ground state is of order 10 nanometers or so, which I told in the beginning. Now, what is important is to find out how one couples these motional modes by exciting the internal state of the ion. To do that, the treatment is basically you look at how the laser interacts with the ion and the total Hamiltonian, the unperturbed Hamiltonian of the atom and the interaction Hamiltonian. So this is the Hamiltonian of the ion in the trap, the kinetic energy and the potential energy. And these are the operators for exciting the ion to either the internal state or the motional states. And you can write the interaction Hamiltonian, which is like a James-Cumming Hamiltonian, where the sigmas are the Pauli spin operators for the internal states. And you get a parameter which is basically called as a Lamb-Dickey parameter, which is very important for this because the extent of the wave function is much smaller than the wavelength of the light that is interacting. And that decides how much coupling you can get when you go from one harmonic oscillator level to the other harmonic oscillator level. So this Lamb-Dickey parameter, if you are coming straight on the ion, it's this, but then when you come at an angle, then it scales with the cos theta factor. This k is 2 pi by lambda. So the atom's internal energy level and the motional mode, this is the unperturbed Hamiltonian, and then you come with an interaction Hamiltonian, which is basically your light with a frequency of mu L. And this eta is the Lamb-Dickey parameter that I talked about, where A and A daggers are the creation and annihilation operators for the motional modes of the ion. Now you do all that, and then you get the coupling strengths for the carrier, for the red sidebands and the blue sidebands. For the red sidebands, it's a James-Cummings Hamiltonian, which I told you, it comes like this. So you couple from basically a higher excited level in the harmonic oscillator to a lower excited level. And the blue sideband is when you couple the atom from the lower excited state, a lower energy level in the harmonic oscillator to the higher energy level. Now, from here, the coupling strengths basically for the carrier, which means when you are not exciting any motional mode, is basically if you are, depending on which level you are in the harmonic oscillator n, it scales as 1 minus this Lamb-Dickey parameter square times this n. So if you are in n equal to 0, the lowest vibrational state, the coupling is the highest. Now for the red sideband, it goes as square root of n. N is the harmonic oscillator energy level. And for the blue sideband, it goes as square root of n plus 1. Of course, there is Lamb-Dickey parameter here. So the coupling strength depends upon the Lamb-Dickey parameter. The higher it is, the coupling is more, basically. Now, how do we go to the ground state of the harmonic oscillator potential? Now, when you cool the ion, the energy is still high enough, although it is much lower than the Coulomb energy between the repulsion energy between the ions. You may be still in the superposition or some kind of a coherent state of all these motional modes, because your ion is basically, the kinetic energy is still, it's occupying the higher excited states in the harmonic oscillator. It's in some coherent superposition of all these harmonic oscillator levels. In order to take it down to the lowest energy level, what you do is that you look, if we look at the ladder of energy level diagrams, one second. So this is the ladder of this energy level diagram. So if my ion is somewhere far up here, it will be occupying in one of these energy levels in the ladder. Now, if I come with a red sideband, what you basically do is that you excite from this ground state to the internal excited state, plus you are actually, when the photon is emitted, it basically, the energy of the emitted photon is higher than the internal higher than the energy of the photon that you are exciting it with, because the extra energy is coming from the motional mode. And then you go to, say, if you start from n equal to 3, you go to n equal to 2. And by successive absorption and emission cycles of the photons, you go from higher energy levels to the lowest possible one. And from there, there is no more it can be coupled to any more level below it, because there is no more level. So you end up in the ground state. So this is called as a sideband cooling. Now, for this sideband cooling to work, there are a couple of conditions. First of all, the laser that you are using to excite, the laser frequency should be much larger than the line width. This line width has to be much smaller than the laser frequency and the excited state decay rate. So these are the conditions that you need to satisfy to do the sideband cooling. And you can calculate the cooling rate and see how many photons are needed for going to the ground state by putting in the numbers for the lambda key parameters and the coupling strength of the laser omega to the internal state and the decay rate of the excited state gamma. Typically, the experimental setup with minimal optics looks like this. So you have a vacuum chamber, you have the trap inside, then you have a radio frequency that is applied to the linear electrodes, and a DC electrodes, DC voltage applied to the end caps. And then there are some additional electrodes for compensating the micro motion and reducing the micro motion. And then you have a big lens that collects as much light as possible, basically a large numerical aperture lens, and then you focus it onto an intensifying or electron multiplying CCD camera, or you can put it on a photomultiplier tube or an avalanche photodiode to do to measure the photons that are emitted from the atom, from the ion. And this is the trap. This circle is about 2.5 inch, and then you have the trap electrodes, axial electrodes, and these are the axial electrodes, these are the radial electrodes, and you have a linear chain that is formed here from where you image the ions. And once you have a string of ions, all you need to do is, depending upon whether you are going to use the microwave qubit or the optical transition, you choose your laser, which you focus onto each of these ions, and you can move the ion from move the laser from one ion to the other to address each of these ions very specifically. Or you can move the chain of ions in a surface trap. You can move the ions and bring them in the zone where you are bringing your qubit manipulation laser, and then you make the light interact with the internal state of the ion, and then you do all the qubit state manipulation. So the carrier transition is going to give you the Rabi oscillations on the S and D transition. These are the single qubit gates, and you apply these blue sideband pulses. This will allow you to, if you had more than one ion, when you excite a motional mode, both ions are going to move. You apply a blue sideband pulse on one ion by focusing light onto it. Even the second ion starts moving. So this is how you get the interaction between the ions, because there is a Coulomb repulsion between the ions. So that is what is used for doing two qubit gates. And then you can do many things, like you can do two particle Bell states, you can apply this universal Dirac-Zöller gate, you can do multi-qubit entanglement, and you can execute quantum circuits on multiple qubits for doing the quantum computing. Now, I'll show you just one example about how two qubit gates are implemented for two qubit operations are implemented, for example, creating an entangled state of two ions. So the Bell states, when you have two ions, so the two ions, so this is a superposition of both ions in the ground state and both ions in the excited state. This is one of the Bell states, and then you can have one in the ground, one in the excited, and the other in the ground and the other one in the excited state, and so on. So you can create these 4 types of Bell states: SS plus DD, SD plus DS, SS minus DD, SD minus DS. So these kind of Bell states you can create, and I'll give you one example of how this is done. So for 2 ions, the way this Bell state is created is, first you prepare both ions in the ground state of the motional mode. That is 0 here. So this 0 denotes the motional mode. SS, this is the state of these 2 ions. Both ions are in the ground state. Now you come with a laser, point it on this ion, and initial state is this. So you point this laser on ion number 1, and then you give a blue pulse, which is of pi by 2 duration, so that you create a superposition of this S0 and D1. So basically there is a motional mode, plus there is this ion is in a superposition of its own internal ground state, whereas both ions, since they are coupled with Coulomb repulsion, both of them will start oscillating in the first excited state of the harmonic oscillator potential. So you get this state SS0 plus the first one is basically the first ion is in a superposition of S and D, and the motional mode is also in a superposition of 0 and 1. Now what you do is that you move that laser point it onto the ion number 2, and you apply a pulse on the carrier. You don't excite any motional mode. So what you do is that you change this S to D. This S has become D on the second ion, but it is also again in a superposition of this state. Basically, it will be in D state, but it is also in the superposition of 0 and 1 motional mode, because you didn't take away the motional mode. Both ions are still in the first excited state, a superposition of first motional excited state and the ground state of the motional modes. Then now the third pulse should be to take away the motional mode. The way you do that is you remain on ion number 2, and then you apply a blue pi pulse. So this state will come to here. So this D changes to S, whereas this D, when it is in this motional ground state, it has nowhere to go because there is no state below that. So you generate this state. So you have SD plus DS, and you are back to the lowest motional mode. So you factored out the motional mode by applying this pi by 2 pulse. Now you can then do a tomography of the state, complete tomography of the state, and you can get, these days the fidelities are much higher than this. They are close to 99%, more than 99%. These are older results. So the way this pulse sequence is denoted is, you take this starting state, this is the initialized state, both ions in the ground state and in the motional ground state also, and you apply these pulses one by one, going from here, the first pulse, blue pi by 2 pulse on ion number 1, then you apply a pi by 2 pulse on pi pulse on ion number 2, carrier pi pulse, then you apply a blue pi by 2 pulse. So the 3 pulses in this opposite sequence, you generate this state. Now if you change the phase of the last pulse to minus pi by 2, then you change the sign of this. You make it SD minus DS. And you can similarly, by applying these pulses here, the last one is a pi pulse and the first pulse has a negative sign, you can create this state, SS plus DD. You can also create SS minus DD, and so on. So these are 2-qubit entangling gates. Okay, this is an earlier version. So the state of the art right now, Continuum has 98 qubits one, which was released only last year, end of 2025. But this was the earlier version, the 56 qubit version. You can see the fidelities of these gates. So single qubit fidelities are like 3 times 10 to the power minus 5 or so in fidelity. So 1 minus this will give you the fidelity. So these are very, very high. And these can be connected. Every qubit can be connected to every other qubit, and you can do parallel 2-qubit gates and so on. Now they have a better version. I forgot to add the slide of the latest one. And then there is so this one, the Honeywell, the Continuum version is a surface trap, but the 3D trap version is from Alpine Quantum Technology from the Innsbruck group, where I had worked long ago. They have now little over 20 qubits, and their fidelities are also more than 99.96% in this. Yeah, thanks. I can take questions now. Yeah, I think I have to read from the Q&A box, right? Okay. Okay, the first question is, why is qubit always initialized in 0? Well, depends what computation you want to do. So sometimes some qubits you may want them in 1, sometimes you may want them in 0. Depending on what kind of quantum circuit you are executing, you can initialize it in 0 or 1 or even a superposition of 0 and 1. Okay, what are the tested and available mechanism to read out the qubit state? Okay, the way it is read in case of ions is what I had showed you. So whenever the electron is in the excited state, the D state, which is 1, you shine the blue light on the auxiliary transition. There won't be any scattering of light because the electron is somewhere else. It is not in the ground state. So if there is no light, then you know that the qubit is in the excited state or 1 state. But when the electron is in the ground state, which is your 0 state, then you know that, okay, if you see light, then you know that it is in the ground state. Okay, how can you please explain the geometry of the spherical Paul trap and how is the saddle potential being generated? Okay, so the spherical Paul trap is nothing but a ring and then 2 end caps, one on top and one on bottom. So you apply, say, if you apply a DC potential between the center electrode and the upper electrodes, the outer 2 electrodes, say if the center one is negative and the outer ones are positive, then if you draw the field lines, they will go from the ring towards the end caps. So when you put a charged particle in there, it will go in one direction but not in the other direction because the field lines are pointing in one direction. But if you flip the sign of the field, then the charged particle will go towards the ring now. It won't go towards the end cap. So that's what is the saddle potential. So in one direction, it cannot move, but in the other direction, it can go away. Can the heat generated during cooling down the system be used as feedback? It depends on what feedback one is talking about, but mostly the light that is emitted during the cooling process, it's basically a random light. The photons that are scattered from the atoms during laser cooling, they are basically completely incoherent and they carry away the energy, extra thermal energy from the atoms. But if you are looking at the photons that are emitted during the coherent drive of the on the say qubit transition, indeed people use those photons for feedback. Is the long stop 729 nanometer is higher? That's why we can't see this. No, 729 nanometer can be seen, but one blocks that light. One is interested in looking only at the blue light in case of this calcium ion. There are other ions, there are other detection schemes and wavelengths, but for this particular ion. When you are doing the detection optically, it is the 729 nanometer, that is the qubit transition, but detection is with a light which is close to 400 nanometers. In calcium 40, if they are from the same ground state, how is it ensured that we get the 729 nanometer transition and not the other short-lived level when the electrons are excited? I didn't quite well understand this question, but let me tell you from what I understand. If you are asking, see, 729 nanometer light is used to excite the transition to the long-lived level. Okay, and for the short-lived level, the blue light is used. Now, you do not use both lights at the same time. For example, when you are doing the qubit manipulation cycle, you are not shining the light on blue light on the ion simultaneously, because then your electron would get excited to the short-lived level. It will not get excited to the long-lived level, because the short-lived level has a stronger coupling to light because it's a dipole allowed transition, whereas the coupling to 729 nanometer is much weaker than the other dipole transition. So if you have the blue light, you will never excite the qubit transition. How are we encoding information in ion? How is it different from classical encoding? Okay, so first of all, the state of the electron, the two levels in which the electron is, those are the qubit states. Now, when we are talking about quantum information processing, we are using the principles of quantum superposition of the, quantum states. That is, in this case, the electron state in the ground state and the excited state. And that is where you are encoding the information in terms of the superposition when you are of the internal states when you are talking about a single one. So that is different from a classical encoding, because in a classical computer, you have only two possible states, two voltage levels, predefined voltage levels, depending upon what logic standard you are talking about. You are using either TTL or ECL or something else. There, the encoding is done by either switching on some transistor or switching it off at the core fundamental level of the gates when we are talking about gates in a classical computer. In the quantum case, you have the two-level quantum mechanical system whose superpositions are used for encoding information. Okay, it's about laser cooling. I heard William Phillips, the Nobel laureate on laser cooling, and he said that there is scope for work in neutral atoms. How can we differentiate with charged atom in our, and also laser beam can help the ions to structure them in different. Can you put your opinion on them? Okay, if you mean that there is scope to work in neutral atoms, yes, indeed, neutral atoms are being used now for building quantum computers, and in fact, in terms of scalability, they are the best, because one can trap thousands of these. People have shown trapping of over 1,000 atoms in an array of optical potentials. And in case of ions, the patterns, definite patterns, are typically formed naturally after you reduce the energy of an ion cloud with laser cooling below the Coulomb energy. And all these ions, they rearrange themselves depending upon how tightly they are confined along the radial and the axial directions. They form very beautiful and nice patterns. Quantum roadmap slide. Did I have the quantum roadmap slide? Okay, I'll share it later if I have one. So calcium 2 plus is more stable, then why are we taking calcium ion? I don't understand what is the meaning of stability in this case, because if you go to calcium, if you go to higher ionization states, then the energy levels of these electrons are completely different, and you may have to find a suitable qubit transition in that, and the the more you ionize the atoms, the the outermost electron is more tightly bound and the energy level separations are much smaller, and the wavelengths that you may have to work with will be much smaller than visible wavelengths. So it might become much harder. In the Lambda-Dicke parameter, angle theta is measured with respect to what? With respect to the motion of the ion. Say if it's along the axial direction, the axial frequencies, the Lambda-Dicke parameter for the axial modes, that's what is going to be the case. So if it is blue instead of red, will it be from lower to higher in that case? Yes, indeed it is. So if you excite with laser light whose frequency is higher by just about the amount of the harmonic oscillator energy levels, then you not only excite the internal state, but also you excite the motional mode. So the total energy of the laser should be equal to the internal energy level difference plus the motional mode energy level. I have seen quantum computer at TCG Crest. Okay. So Xanadu is also working in this domain. Okay. I don't know. I think Xanadu is probably working in with photons. I'm not aware if they are working with ions. When do you think the realization of usable quantum computer? I mean, are we near to achieve it or perhaps in 10 years? In 10 years for sure. How near are we? I can't clearly comment on that at the moment. In microwave-driven ion traps, what are the principal theoretical limits on crosstalk suppression in high-density electrode arrays, and can optimal control sequences? Okay, so typically when you have a microwave transition, a qubit with the microwave in the microwave domain, for example, the hyperfine qubit, they are not directly driven by microwaves, depending upon whether you want to address all of them or whether you want selectively address one of them. Typically, laser pulses, Raman transitions between these two levels is used. So you have two laser pulses, laser beams, whose frequency difference is exactly equal to the frequency difference of these two hyperfine levels. So what happens? You drive a Raman transition from one ground state to the other hyperfine ground state. So the addressability will be limited by how well you can focus the light and how far the ions are from each other, the neighboring ions. If measuring a qubit causes its separation to collapse into a definite, how is it possible for a quantum algorithm to perform calculations on multiple values at once without? Okay, so measurement sequence is what you do towards the end of applying all the coherent manipulation operations. So all the gates that one talks about are either single qubit gates or 2 qubit gates, right? So when I do a single qubit gate, I am coherently exciting that particular transition, driving that particular transition from a ground state to an excited state or vice versa. There, since the laser that is driving has a very well-defined phase, with respect, and the phase coherence of the laser is not lost during all the operations. Between consecutive operations, there is no loss of within the limits, technical limits of the lasers and also the environment of the ion. There is no loss of quantum information. But as I told you, once you finish all your coherent manipulation operations, when you shine the blue light is when you are making the system collapse onto one of the states, depending upon with what probability that particular state was in any superposition or whatever state. For surface code fault tolerance in segmented ion, what trap capacity regime small yields the optimum trade-off between logical error? Okay, I am not an expert in this. I cannot comment on this question. How is the image of ion string generated? It is not generated, it is the image that you see. It is the camera that sees the ions. In fact, if the light were in visible range, like in barium ions, where the light wavelength is green, if you make the room sufficiently dark and you look into the trap with a microscope, you can see the fluorescence from the ion. So it is a real live image that you see on the camera. Okay, I don't understand this question, sir. In 00, U takes SS plus DD. But in 10, U takes SSDD. It should be come in 11. No? Okay, I didn't understand that question. I have a question regarding quantum entanglement. When we say two particles are entangled, let's say one electron is at Earth and the other one, through any means we know about the spin of. Okay, I refrain from answering this question. If I shine a laser at one ion in a crowded memory zone, how far away do the other ions need to be so that they don't get messed up by the light? Okay, so in this case where you have a string of ions and you want to address only one ion in the middle, your laser beam focus should be sufficiently small so that even after focusing to a Gaussian beam spot, there will be some light which will be still there towards which falls on the neighboring ion. So that will lead to some addressing errors. But during addressing, so that has to be, so you have to have this ion sufficiently further away and also the light to be focused very tight. And also there are means to correct these addressing errors on the neighboring ions by shining another light which will cancel the effect of this light. Which architecture is more advantageous when considering scalability, maintenance, fault-tolerant qubits? It will be a two-dimensional architecture, two-dimensional surface trap. So can you explain quantum jump briefly and what is the significance in qubit? Can we use this technique for making In fact, quantum jumps is the technique that is used for measuring the state of the electron. So once you put the electron in the metastable state, it's going to remain there as long as the lifetime allows or any interaction with the environment makes that electron decay to the ground state.
Thank you, Professor. Thank you.
Yeah, thanks a lot.
So, have a good day, Professor. We are done for the day. Thanks a lot.
Thank you. Bye.
Good night.
The recording has stopped.